This battery is big enough to start a car, but I'm gonna do it with these. Well, not just these, thousands of them. They don't look like much, but careful stacking can make high voltage plasma or something more useful like starting a car. In this video, I'll teach you the fundamentals of voltage and current, then use them to run experiments on stuff around the house. Several billion of these things are consumed each year in remotes, key fobs, and the occasional explosion. Yeah, turns out that warning on the package is right. But don't worry, I'm using a bench power supply to put them in a condition that's highly unlikely in your pocket. Generally, coin cells are pretty safe. It's fun to stick flashing LEDs on them with magnets and toss them in odd places around the house for parties. They'll also stick to your car, but I wouldn't recommend it in case other drivers get the wrong idea. To see what's inside, let's carefully open a few with my mill. Though there's some variation across brands, what's common is soft lithium metal stuck to the negative side in a big black chunk of manganese.
Apparently you can't let those two come in contact with each other. That's what the membrane's for.
I read online that direct contact risks of fire, but after multiple attempts, I get nothing. The only excitement is from dumping the lithium in water to release hydrogen gas. But unlike pure sodium, I have to light it myself. Now that we know what's inside, what's the best way to stack these things to power a car? Let's try some combinations with LEDs to see what works best. In the middle is a single LED on a single battery. On the right are two batteries connected side by side on a copper sheet, also with a single LED. On the left, we're stacking two batteries like sandwiches with an LED. Now take a guess which one you think will last the longest. We can see the one on the left starts out much brighter than the others, but it doesn't take long for that to change. After 4 days, the one on the left is the first to go completely out. But it had two batteries while the middle had only one. To understand why, we need to know the difference between volts and current. If we imagine this little cup as a 3-volt battery, then just like batteries, we could stack these for higher voltages. Down here we would have 3 volts, then 6 volts, then 12. Connecting the bulb at each level, we see that 12 volts is the brightest, then dimmer and dimmer as the voltage drops. That's why it helps to think of volts as electrical pressure. The higher the voltage, the more current gets pushed through the bulb, making it brighter. Also like batteries, placing the cups side by side leaves the voltage unchanged, but doubles how long it will last. Eventually, we get to one wide cup at that same voltage. We've added one on each shelf, matching the electrical pressure of that shelf, but with longer life. And it's the same with real-life batteries. For a given voltage and chemistry, the bigger they are, the longer they'll last. Now I realize these tiny ones don't look like much, but if you check the label or measure them, you'll see that they deliver the same 6 or 12 volts of pressure that the big ones do. Cutting them open, we find that stacking batteries for higher voltage is something manufacturers do, just like we did with our cups. But sometimes we see a big car battery and think, wouldn't that just cook a tiny little bulb like this? But no, so long as it's the right voltage, it simply lasts longer than the smaller ones on the same shelf. So wait a sec, if a higher voltage shelf pushes more current, would a lower voltage shelf push less current and increase life? Yes! We saw that on our LED time lapse. Lower voltage pushed less current through the LED and lasted much longer. But if we section our biggest imaginary battery, we see that even at 12 volts, the little bulb sips so little current, it would seem to run forever. That's why they make good dome lights in a car. If they're left on accidentally, the car will still have enough juice to start the next day. But headlight bulbs are a different story. They're way more powerful, so they draw way more current. Leave those on all night and even a big car battery will run low. That's why car batteries have such big wires. Like a big straw, the wires have to be big to handle all that current. So to mimic a 12-volt car battery, clearly we need to stack our 3-volt batteries 4 high. But how many will we need side by side? This CR2032 battery spec shows a max current of 0.2 milliamps lasting 10,000 hours. But I've found if you only need it for a few seconds, you can get a lot more. I used a potentiometer to discharge several batteries and was able to briefly get 150 milliamps. When I ask Google how many amps an automotive starter needs, it says 100 to 150. That tells me we need about 1,000 of these batteries stacked 4 high to start a car. But wait, when I take 150 milliamps from the batteries, the voltage drops below 2 volts. So I better add a 5th battery to prevent the voltage from going too low during cranking, which will make for a total of 5,000 batteries. My idea is to 3D print plastic bricks to hold a 5 by 5 by 5 matrix of batteries with copper plates at the top and bottom. By my math, 40 of those bricks would total 5,000 batteries. But checking the price for custom cut copper plate, it doesn't have an option below 1 millimeter thickness. 80 plates at that price would be way too much money. Fortunately, I have a way to turn my mill into a CNC plasma table. I've ordered a roll of thin copper sheet, but it's quickly becoming apparent why the supplier didn't want to mess with anything less than a millimeter thick. The copper heats up while cutting and flexes all over the place. I eventually got one cut, but the fit isn't great and there's non-conductive oxide everywhere. Time to totally rethink my design. My first design had little posts between the batteries to keep them from sliding out of position. Though rare, there have been instances where loose coin cells shorted out on each other and exploded. But eliminating those posts simplifies the copper, allowing me to cut it by hand. So I'm just planning to be super careful during assembly. I figure I need some holes for clamping screws in the middle, so I printed a fixture for plunge cuts with an end mill. And to eliminate the chance of a single battery not making contact, I'm adding dimples to the upper plate to act as springs. Forming metal with 3D prints is really handy. This tough 2000 resin even withstood getting pounded with a mallet. I'm starting to get serious about putting these battery packs together because obviously I have to make a bunch of these things. I adjusted the 3D print fit so that it would hold the batteries more snug, and I went a little too far. As I was putting this guy together, the batteries were getting kind of tight and sort of lifting up on each other. I start checking the voltage. I'm getting 16.18 volts, but this other one that I put together several weeks ago as my first test is still up at like 16.6, half a volt higher than this one is. It doesn't sound like a lot, but when I start stacking these things and putting them all together in parallel, that half a volt is going to be pulling a lot of current to this particular brick. One, taking it from the others that I need to start the car, but two, you saw what happened with these batteries. I don't want to be sending current into these things that isn't supposed to be going in there, making something that's going to go boom on me. I need to be a lot more careful. I put this thing on the mill, cleaned it up. The batteries fit in there a lot better now. As I take one out and measure it, it's a little below the 3.3 that they are out of the package. I think all 125 of these are a loss. I have to ditch them and start over and be a lot more careful about putting these things together. After discovering how easy it is to short a single battery, I started measuring the voltage of every battery in every layer. Turns out it wasn't always my fault. One battery measured a minus 0.2 volts, meaning slight opposite polarity. I milled off the crimp and opened it up to discover what looked like no lithium on the anode. But when I dumped it in water...
Oh, there's lithium there, just not very much.
So something went wrong with the lithium application process at the factory. I also figured it would be a good idea to measure what my car actually uses when starting. Turns out it draws significantly more than 150 amps. But 180 amps will require 8 more bricks, bringing the total to 6,000 batteries. I knew this would be a lot of work, but it's hard to appreciate just how much until you're in the thick of it. Seemingly endless printing, fabrication, assembly, and testing over and over for weeks. It was a joy to take a break and weld the structure to support all the nested bricks. But eventually they were all done and ready to assemble. I should mention I designed all of this in Onshape, and if you give me a sec, I'll tell you why. There's a frightening amount of energy here, and Onshape's bottom tabs are the fastest I've seen for quickly flipping between parts and assemblies looking for errors. But the biggest reason professionals should try Onshape is collaboration. In most CAD systems, engineers are forced to take turns working on parts, checking them into a vault every time someone else needs to tweak it. I did this for years and it sucks. Whereas in Onshape, I've literally edited the same parts and assembly simultaneously with another engineer thousands of miles away while on a video call with them. It was just like editing a Google Doc. Why should CAD be any different? Now, there is a free version of Onshape that anyone can use, but if you're an engineer, you and your coworkers can try Onshape Professional for free for 6 months while you decide if it's as good as I'm saying it is, using it on your own projects. Just see the link down in the video description. After painstakingly connecting all the wires, it's finally ready to go. It's done. This is the most ridiculous thing I have ever built. 6,000 coin cell batteries, CR2032s. I have this switch up here, this disconnect switch, 3, 2, 1, connecting, and we are at 16.77 volts. But I did run into a problem as I was connecting all of these bricks in parallel. I was of course checking the voltage to make sure that everything was balanced. All of the bricks except one came out between 16.77 and 16.75. I felt very confident connecting those, the grounds to the grounds and the positive to the positive in parallel. There was one brick that was down at like 15 volts. Let me show you that one after I disconnect this. Safety. This one right here, 15.73, a whole volt lower. You remember I did have some problems stacking some of these batteries. A couple of the bricks, I had to take them all the way back apart and restack it because these coin cells are so easy to short out. The positive and the negative are right next to each other. You just touch something metal like that and you can short it out. It loses a bunch of its life. All of a sudden, all the other batteries are fighting. At that low voltage, that must have been more than one, so I don't know. I don't know what I did, but I'm not gonna let it take down the rest of these. I was nervous whether 6,000 coin cells would be enough to start a car. Now we're gonna do it with 5,875. Okay, before we do this, I wanna show you something that I've noticed on this car. I do all my own work on my vehicles to save money. Whenever I take the battery terminal off and then reconnect it, if I just try to start this car right away, watch what happens. It runs and then it dies. And I had to figure out how do I keep it from doing this with the coin cell test. It turns out, fresh reset. Now I'm gonna go to the on position with the key and give it the count to 5. Key in the on position, 1, 2, 3, 4, 5, good enough. And it runs. No problem. So I have to remember to do that when we actually do the coin cell so it doesn't look like it didn't work. I am concerned our 16.77 volts might be high enough to damage the car's electronics, but if that were the case, a faulty alternator voltage regulator could do it. One last check shows how high the alternator sometimes takes it while idling in the driveway. Over 14 volts just sitting here idling. We'll see if it can handle 16.7. I considered disabling the alternator to ensure it wouldn't try to charge our non-rechargeable coin cells, but our battery voltage should remain high enough that the alternator won't try to engage until I disconnect our battery. Okay, for some reason we aren't even connected and we're at 0.37 volts, but no current going through. I'm terrified. We're just gonna do it anyway. On. How many volts do we have? 16 point something. All right, Quint, don't forget to turn the key on and count to 5. Hopefully the voltage isn't frying anything. Counting to 5, everything's turning on. 1, 2, 3, 4, 5. Please start. Yes! All right, turning it off. This way. And it stays on. Okay. All right. We did it. All right. And as we've seen before in my prior videos, even though I have completely disconnected the battery, I'm shaking. Even though we've completely disconnected the battery and there's no battery in the car, the alternator is now supplying the voltage and keeping it at a nice healthy 13 something. So you heard it struggle a bit, but it started. We did it with 5,875 coin cells. And it didn't explode. Yeah, there you go. No current going because it's all coming from the alternator, of course. I need to take a nap. So I just got a chance to review the footage from starting the car with the coin cells, and oh my goodness, going frame by frame, it took 242 amps out of that coin cell battery block at 7.55 volts. So I was hoping to keep it above 9 volts, but it dropped all the way down, 7.55, and then pulled, I can't believe 242 amps came out of that. Now that we've demonstrated peak current, I'm rewiring it for max voltage. All 48 bricks in series add up to nearly 800 volts. I got a little too comfortable with the 12 volt version, so I literally left myself a note to adjust my behavior. I also opted to run a torture test of my first experimental block to see what happens when the terminals get shorted. I was surprised to see an initial burst of 12 amps, which quickly dropped to 2, then 1. The energy has nowhere to go but to convert to heat, so naturally a thermal camera shows the temperature slowly climbing. After an hour, it got to 122 degrees Fahrenheit on the outside, so I decided to end it there. I seriously doubt they would have gotten hot enough to rupture, but a heat gun proves that is a realistic failure mode. But before we start destroying stuff with our 800 volt monster, I want to see what a single stack of coin cells in series will do. The quickest way is to connect them with magnets, which turns out is just enough to burn out an LED. And though I'm aiming for over 1,000 volts, first I want to replicate wall voltage, but with direct current. It should take about 36 batteries to get the 120 volts supplied to the outlets in homes in North America. First test, household, nightlight. This should work. Oh, I accidentally did it. Yeah, 96 volts. But check this out. Plugging that same light into the wall in slow motion, we see it pulses while our battery one does not. This is because the voltage in our walls goes up and down, above and below zero. At 60 Hertz, the voltage goes to zero 120 times a second. But the bulb never goes out because the filament doesn't have time to fully cool. Meanwhile, our battery-powered bulb on the right just sits there constantly on because the voltage and current are stable the whole time. To get over 1,000 volts, we need a bunch more of these. Inserting magnets on the ends makes series connections super easy. But I discovered even a single column of coin cells can shock you when it gets high enough volts. Whoops! Ugh. Don't connect the circuit. Cap on the end. Flip it over. Hey, now, no pain. I got shocked because I hurried, and I hurried because I knew one stack was unlikely to injure me. But soon, this will turn deadly. And if I die, my wife will kill me. Seriously though, the shock did highlight yet another example of series versus parallel I would have otherwise missed. I'm literally getting ready to put the next one together after shocking myself, and I started to think, oh shoot, I've got all these batteries that I'm going to shock myself with. But then, no, we know the difference now between series and parallel. Here, they're in series, and here, they're in parallel. I can just lay my hand on here and I'm not gonna get shocked. Why? 3 volts isn't enough to shock me through human skin. It's just kind of funny to see the difference between what series feels like and what parallel feels like, that I'm not gonna get that shock from these. But 10 of them would give me the last shock of my life. So you'll notice I'm wearing 12 kilovolt lineman's gloves and taking extra care every step of the way. Do not repeat anything I'm doing in this video. Let's see what happens to an LED with 1200 volts. Whoa, ooh, I think I saw a little spark down there as I pulled away. Okay, watching the replay. Oh my gosh. Marshmallow makes fun music, but turns out he's a terrible conductor.
Oh, we're not doing anything to him, are we?
The only action I could get was striking an arc directly off the alligator clips. So to help him out, I soaked the top of his head in salt water. How we doing, Marshmallow? Oh my goodness! Three, two, one. Oh, he's frying. He's burning! Oh no! Plasma on our dome light is really cool. You can hear the first arc pop as it makes contact. Then current flows to illuminate the filament. Then we hear the second arc, but weirdly there's an extra pop sound I can't explain just before it breaks. Let me know in the comments what you think it was. Enough of this puny low current stuff. Instead of 360 batteries single stacked, we're switching to 240 batteries stacked 25 wide. That's 67% of the voltage with 25 times the current. First up is the dome light. Any guesses? Oh my gosh! For the record, the battery dropped to 157 volts at almost 11 amps. Amazingly, the watts are only 6% less than starting the car, proving the power hasn't changed, just the configuration. Hey, bulbs are cheap. Let's do another one.
I no longer have an alligator clip. Wow. Oh my goodness. Just don't explode on me, would you? Whoa! Whoa!
But the most deadly part of these batteries isn't sparks or explosions, it's ingestion. When they contact flesh, a chemical reaction generates sodium hydroxide, aka drain cleaner. It forms a chemical drill penetrating the wall of the esophagus, which is right next to the heart. Though mine didn't make it through this chicken thigh, a moist environment and a little force would have. That's how I got these for free. 3,500 kids a year swallowing them led to mandatory child-safe packaging, making these illegal to sell. A local business offered them up, so I made a PSA while fulfilling my dream of teaching voltage and current the way I wish I'd been taught. And I really want to know if my shelf example clicked for you, so let me know in the comments what you thought. And if you're around small kids, please check their toys or any TV remotes that use coin cells to make sure they have a battery door that can't be easily opened. As for me, I've got lots of cool projects in store, so smash that like button, subscribe if you haven't, and I'll see you in the next video.